everyone, I am Dr. Jagadha, Associate Professor in the Department of Mathematics. The topic for discussion is definitions and terminology regarding Laplace transform. First, we will discuss about definition of Laplace transforms. Next, definition of inverse Laplace transforms. So the more we can say it here, the definition of Laplace transforms. First, let f of t, that is a function f which is defined in the variable t. First, before that, the topic are definitions. The meaning of definition, that is, which is created with some established mathematical laws or parameters. Then the terminology, that is, it is a discipline of systematically which is connected to our definition of that particular subject field. So here our terminology which is subjected to the field of Laplace transform. This Laplace transforms the formulas which are formulated obeying mathematical laws and some parameters. Now, our function f of t, which has the variable t and defined for all positive values of t. Then, the Laplace transform of f of t. So we are writing Laplace transform of, because the mathematician, the name is Laplace, so the transformation which retains its name and called Laplace transform of that particular function f of t, which is denoted by L of f of t. So the capital L of f of t. Here, the capital L which represents, that is Laplace transform of the function f of t. So, mathematically the notation is capital L of f of t, and we will read Laplace transform of the function f of t. Otherwise, which is denoted by f bar of s, which is defined by, that is L of f of t, which is equal to f bar of s equal to integral 0 to infinity. That is, from 0 to infinity, we have to do the integration. Our function, in general formula, we have taken f of t. If it is a problem, what is a function which is given in this particular place, we will replace f of t by that given problem function. So, f of t, which is multiplied by e power minus st, and we have to do the integration with respect to t. So, this is Laplace transform formula. Here, this integral compulsory should exist. That is, depends upon that function. The function should be integrated after multiplying e power minus st. Then only this Laplace exists. Then here s is there. This we know it the t, that is, which is defined in terms of t. And what about this s? S is real or complex number. That is our system of number system. Real number, either natural, whole number, rational, irrational, real. Put together real number system. The square root of negative, square root of minus 1, I, complex. So S may be real or complex number. So, completely, this is the definition of Laplace transform. Easy way to remember: the function, given function f of t, which should be multiplied by e power minus st, and we have to do the integration with respect to t from the integral, the range limit from 0 to infinity. So from this, we discussed what is the definition of Laplace transform. So what type of question we can expect? Define the term Laplace transform, we have to write. Or define the Laplace transform operator. Suppose if the question is asked, we can write capital L. In the formula, the S is playing the role belongs to which number system. If the question is asked, we can answer real or complex. And L of f of t in another form, how it is represented, then this is the answer, f bar of s. And this t, which is defined for either positive or negative values, if it is questioned, the answer is positive values. So the definition we discussed. So different types of the short questions will be asked in such a way. So the next we will move to the operation of multiplying f of t by e power minus st. That is our function f of t, which is multiplied by e power minus st. And we have to do the integration from 0 to infinity, which is called Laplace transform. Now, L of f of t, which is equal to f bar of s. That L we pushed to from left position to right position. Then the L, which has become L inverse of f bar of s. So now the function f of t, which is called inverse Laplace transform. Now this L, we can see it, which is used Laplace transform operator. The Laplace transform is the work what it has, f of t, which is converted into f bar of s. We have to be very careful throughout the Laplace transform, the definitions, f of t, which is converted into L of f of t. This L of f of t is nothing but f bar of s. This is the notation which is given in many of the textbooks. F bar of s. This L is denoted Laplace operator. So L of f of t, which is equal to f bar of s. This L we brought it here, from which we obtained this inverse Laplace transform. So which is called now this capital L, the work regarding f of t, which is converted into L of f of t, is nothing but f bar of s, and we called it as Laplace transform operator. Now the symbol, if you are taking L inverse, the L inverse which transforms just reverse, that is f bar of s into f of t, which is called inverse Laplace transform. Here L inverse, which plays the role inverse Laplace transform operator. So, from this, what we discussed in this slide, what type of questions we can expect? Define the term inverse Laplace transform. We can write it this formula. More, the symbol of Laplace transform. If the question is asked a just one word answer, we can write capital L. What is the inverse Laplace transform operator? L inverse we can write. The L which transforms from which position to which position? F of t into f bar of s. That is regarding L. Then what about L inverse? F bar of s into f of t. So that is the work, the functioning. That is L inverse, which it transforms. That is the transformation is taking place from f bar of s into f of t. So this slide, these many questions, possibilities are there to ask. And one more question also we can expect. The Laplace transform, the integral range value, the limit value from the simple answer 0 to infinity. So next, the slide we will move. Sufficient conditions for the existence of Laplace transform of your function. Now, the function, if you are taking f of t, it must satisfy the following conditions. That is, whether the Laplace transform to exist, what are the conditions? That is, what is the eligibility? The first one is f of t must be piecewise continuous or sectionally on part section continuous in any limited interval. Next, the function f of t is of exponential order. Here, the t should lies between a and b, and everything they are positive. That is, completely this is greater than 0. Piecewise continuous, that we will discuss in detail. A separate slide is there. We will discuss about that. So what is the question from this slide? What we discussed we can expect. When does a Laplace transform exist? So we can write the Laplace transform to exist. It should be piecewise continuous and exponential order. That is the answer to be written. So next, now what are the existence of the Laplace transform? The first condition is piecewise continuous. So the piecewise continuous, it's nothing but we know our Laplace transform 0 to infinity. Suppose the t lies between 0 to 5 and t is greater than 5. If it is given like this, so 0 to 5, so we know 0 to infinity, that is first 0 to 5 one integral and 5 to another integral, but they are discontinuous, but this particular limit it is continuous. Here 5 to 5 t is greater than 5, so it starts from 5 up to infinity. So we can see it very well. So such type of piecewise continuous. So now we can see a function f of t which is said to be piecewise continuous over the closed interval. Here we can see the closed interval a comma b. If it is defined on that interval and is such that the interval can be divided into finite number of sub-intervals. Suppose 0 to infinity is there. 0 to infinity, that is our Laplace transform integral range. So 0 to 5, it is finite. It is a closed interval. Then again 5 to 10. So it is divided into finite number of sub-intervals. But each sub-interval f of t is continuous. That is continuous. The definition is limit x tends to a f of x, which is equal to f of a. So this is the continuous. So the given closed interval, this is the one which is divided into finite number of subintervals, and f of t, that is our given function, which is continuous, and both the left and right limits at every end point of the subinterval. So in the subinterval, if it is divided also, the main closed interval, there also the function is continuous. Then such a continuous function, we will call it as piecewise continuous. Yes. Now, Laplace transform definition, we know it, the formula, which is, that is the terminology which is subject to the field of our Laplace transform, that is integral 0 to infinity e power minus st f of t dt. Now, L of f of t, here I am writing L of f of t. So here exactly f of t is nothing but k. So if the function f of t is, the k is some constant which is given here, the result is k by s. That is, what is a formula which is defined in the Laplace? If f of t is k, then the result is k by s. Here specifically, which is written here, s is greater than 0. It is a positive number. So we can see now, that is from the definition of Laplace transform. So this is our Laplace transform. Easy to remember. The function f of t, which is multiplied by e power minus st, the integration with respect to t, and integrating from 0 to infinity. Fine. Now, what about our f of t? Our f of t is nothing but k. So in the particular f of t, we are going to replace it by k. So the f of t, which is replaced by k. So the k which is written here, thus e power minus st should be replaced it. So e power minus st divided by, we are doing integration with respect to t. So the coefficient of t is nothing but minus s. 0 to infinity. This minus s, we brought it out, and infinity. So in the place of t, we are substituting, we obtained e power minus infinity. So the upper limit, the work is completed. This is the limit formula for the limits, and the lower one is 0. The lower one is 0. That 0, we are going to substitute in the place of t. So e power 0, the value is 1. Yeah, just actually, as it is again written. So we know it very well. This e power minus infinity, the value is 0. So which is kept here 0, and this minus as it is, 1 is as it is. So we brought this minus 1 into minus, nothing but k by s. Specifically, why it is in this video lecture, that is, what is the use of, we defined the Laplace transform formula. This is the one. Suppose when we are solving the problem, we can't actually always, some standard functions are there. If the functions, if they're very different one, f of t place, we will replace it and we will do the integration. But some standard one, that is now L of k. Suppose in the problem, if it comes, we can write it, since L of k equal to k by s, it is treated as some results of elementary functions. So each and everything here substituting in the formula, getting the main formula, what is defined for our Laplace transform, some standard results we extracted. That standard results are, one result is L of k equal to k by s. But in this slide, which is explained that how we obtained the result, the similar manner we can see it, Laplace transform of some elementary functions. L of k, that is our f of t, is k. K by s is the answer. If L of 1, that is our f of t, which plays the role 1, same the manner what we discussed in the previous slide. In our Laplace transform formula, integral 0 to infinity e power minus st f of t dt, our f of t to be replaced by 1. Same procedure if we do, we will obtain the result 1 by s. But while solving the problem, if it comes L of 1, we can write it, since L of 1 equal to 1 by s. Like that, what are the elementary functions are there, we can use it. L of t power n. This is the formula, that is n factorial by s power n plus 1. Next, L of t power n, that is gamma of n plus 1 by s power n plus 1. Two are there. The reason is, suppose L of t square, it is there in case. So n is playing the role 2. If it is positive integers, then we can use this formula. Whereas this n, which is greater than minus 1, are fractions, we can use this gamma function related formula. And L of sine at, say a by s square plus a square, L of cos at, that is our f of t here, cos at. The result is, we have to substitute f of t, replacing cos at into e power minus st. We have to do the integration. We will obtain, this is the result. But while solving the problems, if L of cos at, directly we can apply these sub formulas. These two, this is not any mathematical method teaching, some sort of technique. So many formulas. Is there any easy way to keep in our memory space? Yes, it is there. That is, sine at, we will remember the numerator is dominated by the constant. Cos comes, the numerator which is dominated by s. And between the down, positive sign is there. The reason is one more two formulas are there. Sin HAT. Sin, whether it is sin or sin H, the numerator is dominated by A. Cos or cos H, the numerator is dominated by S. Simple way, easy way, we can remember the formulas. Sin, that is without H, without H, the denominator between the terms positive sign is there. But if H is there, between the terms negative is there. Any formulas, more it is there. How to remember? We should not forget. Such a way, some technique we have to search and have to keep in our memory. Then forever we will remember. Now, important properties of a gamma function, because L of t power n, if that n is fraction or greater than -1, we will apply gamma of n plus 1 by s power n plus 1. That is a formula we discussed. Suppose in case that if it comes in our while solving our problems, this is the notations. Completely in this video lecture, Laplace transform regarding what are the formulas are there, we are going to discuss. So gamma of n plus 1, which is equal to n into gamma of n if n is greater than 0, and gamma of n plus 1, which is equal to n factorial if n is a positive integer. We can see here gamma of 1, which is equal to 1, the values. Gamma of 1 by 2, the value is root pi. Gamma of -1 by 2, which is equal to -2 by pi. Because if the question, that is L of t power n, the gamma formula applying the result, suppose gamma of 1 by 2, if it falls, it should be replaced by root pi. So these formulas very, very important. So now the formulas what we discussed it. L of cos AT. That formula we discussed it. L of cos AT. Only one trigonometric term is there. Answer is s by s square plus a square. While writing only in my memory, it goes, cos is there, numerator, it should be dominated by s. Without h it is there, so compulsory here between positive sign should be there. So by practice, we will write it. We won't get any careless mistake. Now in case L of 1 plus cos AT is there. This is the, in case if it is there, this we want to Laplace. L of cos AT separate if it is there, we have the formula. L of 1, 1 by s, that also we discussed. If it is L of 1, formula it is there. If it is L of cos AT, formula is there. But L of 2 terms, there is no formula. So, the property which is defined using our Laplace transform is linearity property. So the basic concept of our linearity property is Laplace transform of two or more any functions separated, Laplace transform of each function and their sum we will be doing. So we can see it here. So now here we can say it L of f of t, that is the notation is f bar of s. This is one function. Next L of g of t, which is equal to g bar of s, that is another one. L of one function c1 f of t. For a single function, we have some formulas we discussed: sine, cos, t power n, 1, k, sine h, cos h. This, if it comes, we are very comfortable. But even what we know, those formulas also, either it is trigonometric term or the constants combining, if they are coming as two terms, then Laplace transform of first term, that is c1 f of t, in general, we are taking the first term as c1 f of t, the second one as c2 g of t. We can separate, that is, we can able to write c1 Laplace of first term, c2 Laplace of second term, and L of f of t, we know the notation, that is f bar of s. Next one, c2, that is L of g of t, it's nothing but g bar of s, where c1, c2 are constants. So we can see this Laplace definition which is applied here. So Laplace of, this is our function, c1 f of t plus c2 g of t. Laplace transform, that is, the formula is integral 0 to infinity. What is our function? We will write. Yes, we have written. That should be multiplied by our e power minus st, and we have to do the integration with respect to t. Completely, we applied our Laplace transform formula, our function. Now, the integral here, this is integral one time. For this, the second time. Here we can see it here. That is integral 0 to infinity e power minus st c1 f of t dt plus integral 0 to infinity e power minus st c2 g of t dt. So which is here we can see it, which is kept once again. This is the first integral, here is the second integral. The first integral, we have taken the c1 outside. The second integral, c2, we have taken outside. After taking outside, we are noticing this is nothing but our Laplace transform. c1 L of f of t. c2, this is nothing but our Laplace transform. The function is g of t. That's what which is written. This notation, L of f of t, notation is f bar of s, and L of g of t is g bar of s. So what is the basic concept of our linearity property? On what basis which is defined? We defined the linearity property, Laplace transform of two or more functions. We can write it, the sum of each function in the form of Laplace transform. So now, the next actually, so far we discussed about Laplace transform definitions, some important elementary functions, and linearity property. Now, Why Laplace transform, which is very useful for the solving linear differential equations. Laplace transform, which is very useful for solving the linear differential equations, because suppose the derivative we are finding nth derivative. If any other thing, the derivation is complicated to do to solve the differential equations, more time spending factor and complicated also will be there. Whereas while using the Laplace transform, that is nth derivative of f, easily it can be transformed. That is, our f of x can be transformed in a very simple manner. That is the differential equation using the Laplace transform. It is very easy one, because in another way also it is there to find the general solution. Their CF plus particular integral, it is compared to that Laplace transform, which is very easy. Now, we can describe, that is the use of studying Laplace transform. This type of questions we can expect regarding Laplace transform. That is Laplace transform, which is very much useful in obtaining the solution of linear differential equation, both ordinary and partial, and a solution of system of simultaneous differential equations, and solutions of integral equations, solutions of linear difference equations, and in the evaluation of definite integral. So these many roles our Laplace transform is playing. That is what the studying of Laplace transform, which is very important. So this property already we discussed, and how we obtained. To obtain this linearity property, what are the steps we followed it? What is the study which is connected to get this linearity property? So we allow the first one, C1 f of t plus C2 g of t. It's nothing but C1, the first function Laplace, plus constant C2, Laplace of second function. Our first function name is f of t, second function name is g of t. So the next, the Laplace transform formula using first shifting theorem. So if we are taking the first shifting theorem, that is L of f of t, we know the notation, which is f bar of s. If that f of t, which is multiplied by e power minus at, then, which is very easy one, only this f of t only we will apply Laplace. So thus we have to find the Laplace. Easy way, L of f of t. This we won't apply. We will apply this first shifting theorem. That is, S is tends to, here minus a is there, just opposite we will write it. L of f of t, after applying Laplace, the result will be in terms of s. We have to agree. Already we discussed it. L of 1, the result 1 by s in terms of s. So if it is L of e power minus at f of t, that is L of f of t, their s is replaced by s plus a. L of f of t is nothing but f bar of s. S is replaced by s plus a. So we can see it here, s plus a. In case, suppose, instead of e power minus at, if it is e power at, then which will become here s minus a. That is, s is replaced by s minus a, just opposite signs. If it is here plus, here minus, here plus, easy to remember. So here in this slide what we discussed, we can expect state linearity property. Then we can write this property condition. If it is asked, write or state first shifting theorem of Laplace, this formulation to be written. Next, the first shifting theorem, how it plays a role. We can see it here. L of, here it is there. The defined formula of first shifting, how it works. This is L of t power n. Already we defined it, the formula. That is also we discussed it. Only this t power n only, we will apply the Laplace transform formula. This e power at, that is s is replaced by a is here positive, opposite is minus a. So L of t power n, s is replaced by, that is here what we are going to get after applying Laplace, in that in which s is replaced by s minus a. Yeah, this is the formula. Here s is replaced by s minus a. We can see it. Here s is replaced by s minus a. Very simple way we can do the first shifting theorem. But what is the eligibility of it? The function should be multiplied by e power at or e power minus at. So the next one is e power at sine bt. So L of sine bt. Here also we can see it, here positive is there. So here s minus a. This is the sine bt result, b by s square plus b square, in which s is replaced by s minus a. We can see here the condition. Yes, it is replaced by s minus a the whole square, remaining and all as it is written. The third one, e power at cos bt. Only the cos bt, the formula is s by s square plus b square. But here plus a is there. Then s is replaced by s minus a. Yes. Here also s is there. Yes, we have done it. So the fourth one, sin hbt. We can see it here. E power at purpose, the first shifting theorem. That is s is replaced by s minus a. This is the formula for sin hbt. Very simple one. That is, sign is there, the numerator constant. Between the terms, negative sign will be. For this e power at purpose, first shifting, that is, s is replaced by s minus a. Yeah, here it's a constant, only s. So what I am circling, that is, s is replaced by s minus a, remaining all as it is. So the last one, cos hbt, that is s by s square minus b square, is our cos hbt Laplace. For this, s is replaced by s minus a. Yes, it is replaced. Yes, here also replaced. We have done it. What is the use that defined the first shifting theorem to the how it works, we have seen it. So here also e power minus at t power n, the t power n, the formula is n factorial by s power n plus 1. But here minus a is there. So s is replaced by s plus a. So the next also very simple one, sin bt, b by s square plus b square. Then minus a is there, s is replaced by s plus a. And one more thing, in this particular Laplace transform, this integral which plays a role like anything, that's what specifically in the slide which is kept. Integral e power ax sin bx dx, which is equal to e power ax by a square plus b square and a sin bx minus b cos bx. This is the integral formula. And one more also, these two formulas integrals, if it comes in this format, the integration, we can apply this formula and we can evaluate. We no need to go integration by parts or u by v method and all. Just a formula we can apply. These two formulas, they are playing a role like anything. So now e power ax cos bx dx is nothing but e power ax by a square plus b square of a cos bx plus b sin bx. Next, we can concentrate our second shifting theorem. That is, this we know it very well. That is L of f of t equal to f bar of s. This first shifting and second shifting, what is the difference? How they are defined? Is there any differentiation between them? Very simple way. In first shifting theorem, only f of t, only one function. But here, g of t is there. But the g of t, which is connected to our f of t in such a way, that is f of t minus a, if t is greater than a, this is the function. If t is less than a, the function is 0. Then L of g of t, it's nothing but e power minus a as L of f of t. L of f of t, the notation is f bar of s into e power minus as. This is our second shifting theorem formula. What about the change of scale property? That is, here, this is the notation, standard one, L of f of t equal to f bar of s. Suppose, instead of f of t, in the place of t, if it is at, then change of scale property, we can use it. That property is 1 by a. Usually L of f of t we will find. It's nothing but f bar of s. That s is replaced by s by a. That is our change of scale property. So this particular thing, what are the questions we can expect? State second shifting theorem. What is the connectivity between fast shifting and second shifting? And state change of scale property. So every answer, it is there in this slide. So the next one is our f of t, the function which is multiplied by t power n. If it is there, then the formula which is defined for it, minus 1 power n n times we have to do the differentiation. F bar of s is nothing but Laplace of the given function. Suppose the Tn is playing the role 2. We will do the differentiation 2 times, we will find the derivative. If it is our f of t, which is divided by t, then here we can see it, our f of t, which is divided by t, f bar of s, it's nothing but L of f of t. That we have to do the integration from s to infinity. That is the condition for if our f of t, which is divided by t. So the next one is the unit step function, which is defined as h of t minus a, or we can tell u of t minus a. If t is less than a, the function is 0. If t is greater than a, the function is 1. That is, this unit step function at the point t equal to a. So from this slide, what are the questions we can expect? Multiplication by t. If n is t, it has the power 3, then how many times we have to do the derivative? 3 times. If it is n times we have to do the derivative. Then, if it is divided by 2, we are differentiating or integrating? We are doing the integration. If it is one word answer, we have to reply such a way we can reply it. Then, this type of question also we can expect. That is, our h of t minus a. At what point unit step function which is defined? At the point a. So like this, very short questions will be also possibility is there to ask. So the next one is Laplace transform of derivatives. Here we can see it n times it is done the derivative. Yes, it has the power n. If it is n, we will start s power n. It is some sort of technique, it's not any mathematical method. The first term which has L of f of t. If you are noticing regarding s, the power goes on decreasing. N, here n minus 1, n minus 2. The finally one stage here, n minus n, that is s power 0, which is 1. Exponential law, a power 0 equal to 1. And the second term onwards, f of 0, f dash of 0, it goes on. Whether we have written the formula correct or not, easily we can check it. One more, a small technique also is there. That is, here n is there. The formula should end with 1 less. That is n minus 1. The simple one, suppose the second derivative we have taken here. That is, we can see it 2 times the derivative is there. So yes, it has the power square. Here s power 1, it is decreasing. F of 0, next f dash of 0. Here 2 is there, here is 1. So we checked, we have written the formula in a correct way. Next, this is a Laplace transform of derivatives formula which is defined, this one. Next, Laplace transform of integrals. That is L of f of t, that is f bar of s, L of integral 0 to t f of t dt. If it is integral, the final result what we are obtaining, f bar of s, which should be divided by s for the integrals. So these questions we can expect from this, what we discussed on this slide. state Laplace transform of derivatives, state Laplace transform of integrals. The next one is a definition of periodic functions. A function f of t, which is said to be periodic function if the period that is denoted by capital T, which is positive, that is greater than 0, if the function f of t, if it is added with the period also, which is equal to f of t. Here we are adding 2t up to nt, but the original function is 3 times as it is. Such they are called period. Now, this f of t, the given function is, it satisfies the condition of periodic function, then the Laplace transform of that periodic function is integral 0 to t e power minus st f of t dt. So we can see actually, easy to remember, the top one, that is our Laplace transform formula. Only the difference is here in the place of infinity, it is capital T is there. So always we will compare with the formulas how to make the difference. In this formula, what is the variable playing the role, whereas another formula, which variable is playing the role. Here, Laplace transform, here the T place infinity will be there. So the periodic function, the definition which is defined, integral 0 to capital T e power minus st f of t dt, which is divided by 1 minus e power minus st. So this is the question we can expect, that Laplace transform of periodic function. So now, completely so far we have discussed about Laplace transform. Now, the second part of the Laplace transform is inverse Laplace transform. What are the properties so far what we discussed? The same properties under inverse Laplace transform, we can see it. Here, the operator, inverse Laplace operator is L inverse. So L inverse of, here one function, second two functions are taken. But linearity property, basic concept, it never changes. That is, it can be written the sum of each function. The difference only is here inverse operator is playing the role. So we can see it. This is the first function. This is the second function. That is C1 F1 bar of S first, C2 F2 bar of S second. Separate, we can write L inverse of first function, L inverse of second function. So the first shifting theorem of inverse Laplace operator. So L inverse of F bar of S, which is nothing but F of t. So simple way also we can see it, this simplification, L inverse of F bar of S. So far we discussed F bar of S, it's nothing but L of F of t. This both getting cancelled, F of t. This is the way which is defined here. Yes, fine. Now, L inverse of, suppose the function in the form of S minus A if it is there. For the minus A purpose, this e power at. Next, the balance, this L inverse of F bar of S put together, it will become F of t. So there is a doubt in our mind. Instead of here minus A, suppose if it dominated by plus A, very simple. Here plus A is there, here we will write it minus A. So that's what first shifting theorem of inverse Laplace, it works. So what is the possibility of questions to be asked? It is linearity property of inverse Laplace transform, or the first shifting theorem. The second shifting theorem of inverse Laplace transform, that is L inverse of F bar of S, which is F of t. If this F bar of S which is multiplied by e power minus as. That we are assuming as some capital G of t. This capital G of t, what is the connectivity? That is f of t minus a, the t is greater than a, if t is less than a, which is 0. So the result for it is f bar of s, it should be multiplied by e power minus as. If in this format it is there, second shifting theorem of inverse Laplace formula we will apply. The result is f of t minus a into h of t minus a. So this is the possibility of question asking, that is state inverse second shifting theorem of inverse Laplace transform. So the change of scale property is f bar of s is there. If that instead of s, if it is as is there, in such a format, if it is there, then the answer is 1 by a. The t is replaced by t by a, where the a is positive. So the next one is inverse Laplace transform of derivatives. N times we are doing the derivative. So if it is L inverse of nth derivative of f bar of s, it's nothing but minus 1 power n t power n f of t. This is the formula for derivatives under inverse Laplace transform. So what type of questions we can expect here? That is change of scale property or the derivatives questions. Any questions can be asked. A simple way, like this short questions also. Suppose if it is n times is there the derivative and inverse Laplace, the t is having the power. What power? The answer is n power. N times we are doing derivative, the t will have the power n. So the inverse Laplace transform of integrals. Now our f bar of s is there. If it is under integral, that is s to infinity, the result is f of t, which is divided by t. Or this formula, some textbooks, which is written, this t, they brought it here. So this is also the format, t into L inverse of integral s to infinity f bar of s ds. Whatever the problem, suppose in case if it is given, these are the defined formulas. The formula which should fit same format, the problem or what is the question we are asked to solve, it should fit the complete. Suppose if it fits to the left side, the right side, we can apply it. For that, if it is not fitting, then we have to do some modifications mathematically. So next, suppose if it is our f bar of s, this one, if it is multiplied by s, we can see it here. It is given. Yes. If it is multiplied by s, before that one eligibility it should have, that is the function we have to put at the point 0, the value should be 0. F of t, this here, we will apply the t plus 0. If the result is 0, then we will move to applying this if it is multiplied by the powers of s. That is, the answer is the first derivative of t. If it is f bar of s, which is divided by s, we can see it divided by s, then integral 0 to t f of u du. That is our f of t first. We will convert it into f of u format and we will do the integration with respect to u and range from 0 to t. So next to the definition of convolution theorem, that is f of t and g of t are two functions which are defined where t is greater than 0. So we can write here the product of f of t and g of t. So the formula is f of u and g of t minus u du. And we are doing the integration with respect to u and integrating from 0 to t. So, what is a question we can ask? State convolution theorem of Laplace transform. Unit impulse function, that is f epsilon t minus a, which is denoted by delta of t minus a, that is Dirac delta condition, which is called unit impulse function. This, the Laplace transform of, that's delta of t minus a, which is equal to e power minus as. So the possibility of this question, Laplace transform of unit impulse question, formula if it is asked, the answer is e power minus as. So now, so far we discussed Laplace transform and inverse Laplace transform. One thing we have to say, Laplace L of f of t, which is equal to f bar of s. This is the notation we started and we wrote. L inverse of f bar of s, which is equal to f of t. Here f of t, here f bar of s. Here multiplied by t, divided by t, integral, derivative, first shifting, second shifting, everything it is there in Laplace. Here multiplied by s, divided by s, first shifting, second shifting, derivative, integral, all the theorems are there for even inverse also. So first shifting of Laplace, what is the format? First shifting of inverse Laplace, what is the format? If we do the comparison between, strongly we can remember the formulas. Just two formulas we will discuss. This linearity property of Laplace transform. This is linearity property of inverse Laplace transform. Simple way, here L operator is there. Here L inverse operator is there. F of t, g of t. Whereas here f bar of s or g bar of s, we can write it, nothing wrong in it. Here specifically it has taken f1 bar of s, f2 bar of s. But the concept is same. That is Laplace of two functions. Laplace of first function, Laplace of second function. Here L inverse Laplace of two function, inverse Laplace of first function, inverse Laplace of second function. The mathematical notations, L played a role in Laplace, L inverse played a role in inverse Laplace. So all the formulas what we discussed, like this, if we do the comparison study, we will be very stronger. The formulation to remember in our memory, we never forget. So one more also we can discuss, that is comparison between Laplace and inverse Laplace. L of f of t, we can see it here. This is the first shifting of Laplace. This one, first shifting of inverse Laplace. L of f of t equal to f bar of s. Next, this f bar of s here, f of t here, we can see it here. L, it has become L inverse. Here also, this L which is shifted here. Here we have taken A is there. That's what here, minus A. If it is minus A, we will take it plus A. The comparison between the formulas. L is dominated. Here L inverse is dominated. A little differences only will be there if we do the comparison between the formulas. So we will come to a conclusion of this topic, Laplace transforms, in which we discussed the definitions and terminology. So under the established the mathematical laws and the parameters regarding the great mathematician Laplace, he has given the formula to us, Laplace transform, that is integral 0 to infinity e power minus st f of t dt. Then the terminology to get the defined formula, what are the discipline systematically which is connected to our subject field of Laplace transform and inverse Laplace transform. In detail we discussed it. Thank you very much to you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.